How's it going, everyone? Mr. Geyser here with the second video in our Lesson 10B series, where we'll be taking a look at example 8, part A, B, and C, where we'll be transforming some logarithmic functions. In these transformations here, in example 8, we want to describe how to transform the graph of f of x, which equals the natural log of x, or y equals log of x, one of those two functions, into the graph that's given for us in A, B, and C. We want to describe the end behavior using that limit notation. First, in part A, we're given g of x here, which equals the natural log of x plus 2. My first thing that I want to do is I want to try and graph that original f of x function. That way we have something to compare it to. So when we do graph our g of x in blue here, it's almost like we're just moving or pushing or translating this f of x here 2 units to the left. And we know from previous topics that anything affecting our x here really is just affecting it in a horizontal sense. So we can describe the transformation as g of x has a horizontal transformation of 2 units to the left. Now let's try and take a look at the domain and range of these two graphs here. It's pretty easy to see the range for both of these. The range for both of these go down from negative infinity up to positive infinity. But it's the domains that are a bit interesting. If we take a look in the black part here, our domain for f of x starts at 0 and then goes all the way to the positive direction of positive infinity, kind of like a normal log. But because we shifted it 2 units to the right, g of x now has that domain of negative 2 to positive infinity. Range is still all the same. Also take a look at their asymptotes. The asymptotes for f of x here is still x equals 0, but g of x is at that x equals negative 2. That's also shifted. Our asymptote that's in the x coordinate got shifted 2 units. Same thing with our intercept. Our intercept for f of x is 1, 0. Our intercept for g of x is negative 1, 0. However, for our concavity, they're both the same. It both goes down here. But I want to take a look specifically, not just at its concavity, but by describing these graphs. Notice how both of these graphs here are increasing over time. So from x is starting at either negative 2 or 0, the graph is increasing, but the rate of change is decreasing for both of them. As we're increasing larger and larger, our rate of change, it starts really high positive, and then it goes down a little bit less, goes down a little bit less, goes down a little bit less, and we'll explore that in our final example for C. But for right now, we can easily say that both of these graphs are increasing at a decreasing rate because the rate of change is decreasing. So now let's describe the end behavior for both of these graphs here. When we take a look at the left end behavior, our left end behavior is going to have our x approaching 0 for our f of x, because that's its horizontal asymptote, or sorry, that's its vertical asymptote. And for g of x, it's approaching negative 2 from the positive direction. That positive there, right above that 0 and that negative 2, implies it's coming from the positive direction. For our right end behavior, it's pretty simple. As x approaches positive infinity, f of x approaches positive infinity. For g of x here, it's that same limit notation as its parent function here. Now let's take a look at part B. For part B here, we're given that h of x is equal to 1 plus log of x. So really, its parent function is coming from that y equals log of x, where h of x is really just shifted up 1 unit. I'm like pulling that point up 1 unit, which drags the bottom part of this graph here over a little bit. It ends up intercepting at 0.1, 0. And all I really had to do for that was I plugged in 0 into our h of x, not into x, but h of x, and then solve for x there. We can describe this transformation as h of x has a vertical translation 1 unit up. For the domain and range, well, the domain, range, asymptote, intercept, concavity for our y here is all the same from before. Everything is the exact same. Our limit notation is the same, everything. But when we compare it to our new child function, that h of x here, our domain also stays the same. it's still 0, or 0 to infinity in comparison to the parent function. Our range is also the same in comparison to our parent function. So is the asymptote. The intercept is slightly different though. So even though that we have a vertical translation, it still does affect the x in a little bit of a way. Almost as if you grab that, and since you're dragging it upwards, the intercept has to get pulled over a little bit. The concavity, it's still down. The limit notation, we're still approaching 0 from the positive direction for both of them to negative infinity. So nearly everything's the same except for the intercept here when there is a vertical translation. Now, if we take a look at our description here, both of them are still increasing at a decreasing rate because the rate of change is decreasing. Finally, let's take a look at C, where we explore this at the end of our problem. In part C here, we're given that f2 of x, I'm going to change that name for a little bit, is equal to the natural log of 3 minus x, because that parent function for this problem here is that f of x of the natural log of x. So my first step, just like before, is I'm going to graph that natural log of x there, that parent function. And I actually want to try and manipulate my f2 of x just a little bit to make it easier to describe. See how we have like a 3 minus an x? I don't really like it when my x here is negative. So what I can do is I can pull a -1 from both of these terms here, and I end up getting that new function of f2 of x is equal to the natural log of -1 times x minus 3. And it makes it a little bit easier for us to see why this graph here has a reflection about the y-axis. Where now it's reflected about the y-axis, we end up getting two intersections, where we have an intercept here at 2, 0 on our x-axis, and an intersection here where we have it at 0, the natural log of 3. I found this intersection here by just plugging in 0 into where my x was, and then I figured out that it was just going to be ln of 3 minus 0, which is just the natural log of 3. However, for just a little bit of extra credit, I want to see if any of you guys can find the intersection between both of these graphs here. What point is there, or sorry, what point is that where those two graphs meet? Moving along with the problem, we want to try and describe the transformation of f of 2 of x, where it reflects across the y-axis and has a horizontal translation of 3 units to the right. I want to hold on that second part just for a second. In general, when we're looking at the parent function here, it first reflects about the y-axis. So this intersection, this intercept here, ends up going over here at -1, 0, where the graph goes up into that direction, and then it gets pulled back 3 units to the right here. So that's what we want to describe first, the reflection first, and then the translation second. Now we take a look at the domains and ranges. The domain and ranges for our f of x are all the same still. Positive infinity, or 0 to positive infinity, negative to infinity, all that jazz. But let's compare it to our new child function, where the domain and range of our child function is from -infinity to 3, where it's going off to negative infinity. Really, it's coming from negative infinity, and it approaches up to this vertical asymptote at x equals 3. Our range, though, stays the same. This graph here still goes up when it goes into the negatives as it goes down towards x equals 3, so that its range is still negative infinity to positive infinity. Its asymptote here actually happens to be at x equals 3, where the intercepts for our f2 of x is at 2, 0 on our x-axis, and 0, natural log of 3, which is like 1.099. That's where its y-intercept happens to be. Now, the concavity, even though we reflected it about the y-axis, actually kind of just stays the same. It's still down. It's still that frowny face when it comes to that concavity. We can actually write our limit notation in a little bit of a different way. Notice how for our parent function, the limit of x approaching 0 from the positive side, it's limited by that vertical asymptote here. But for our left end behavior of our child function, the blue graph, it actually does go off into negative infinity. So we can say as x approaches negative infinity, our f of x approaches positive infinity. And for here, when we're saying the limit of x approaching positive 3 from the negative side, because we're going from this side to it, when x is approaching 3 from the negative side, f of x, or f2 of x, is approaching negative infinity. Now we want to try and take a look at that rate of change description. Notice how our child function here is going to be different than our parent function. F of x is increasing at a decreasing rate. Its rate of change is decreasing. Still the same from the previous examples. But f2 of x is decreasing at a decreasing rate. And that part here, the decreasing rate, where the rate of change is decreasing, might feel a little bit off for this graph here. I want to go into how we're finding these decreasing rates here. If we just take a look at our child function here, imagine that I'm connecting two different points on the graph by these various looking lines. So this dark maroon graph here is connected from that point here and that point there. We're just drawing a line from it there. That next two graph, or that red line there, is just connected from our point on this point here and that point there. It's just drawing that line there. That next graph is these next 2 points. So we're going from this line, intercepting here, going to there. That next graph is intercepting from here, going down to here. And that final one is going from here to here. And we can kind of see a pattern emerging from these rates of change. Where initially at that maroon line, it was at this rate of change that was closer to like negative 0.5. It's still a negative slope, which makes the graph decreasing. But notice how the next rate of change is negative 1. The next is negative 2, then negative 4, then negative 8. This is a decreasing rate of change. It's not just a decreasing graph, but the rate of change here is becoming more and more negative. It's becoming more and more negative. It's lowering its value, so that's why it is a decreasing graph at a decreasing rate. Thank you very much for joining me on this second video for our Lesson 10B, where we explored the transformation of these three graphs. I look forward to seeing all of you guys in that next video. Take care.